Welcome, data engineers and architects. Let's get started on mastering the critical pillars of Apache Spark security, Kerberos authentication, and data encryption. Welcome, everyone. Today, we are diving deep into how to lock down your Apache Spark workloads. When you run Spark in a distributed environment, your data is flying across the network between the driver and multiple executors. This distributed nature is fantastic for performance, but creates a massive attack surface. If a malicious actor gains access to your network, they could intercept sensitive data or submit rogue jobs. That is why we must implement a zero-trust architecture. The two pillars we will master today are authentication and encryption. Authentication ensures that only verified users and services can talk to your cluster, and we achieve this using the industry standard, Kerberos. Encryption ensures that even if someone intercepts your data over the wire or steals a physical hard drive, the data is unreadable gibberish. By the end of this session, you'll know how to configure both. Take a look at this high-level security architecture. Your Spark application sits at the top, immediately passing through two fundamental security layers. On the left, we handle identity through authentication, communicating with a key distribution center, or KDC, via Kerberos. On the right, we handle data protection via encryption. Notice how encryption is further split into two distinct zones: in-transit encryption, protecting data over the network via TLS and SSL, and at-rest encryption, protecting data on disk using tools like Ranger KMS or AWS KMS. Let's peel back the layers on Kerberos. Kerberos is a battle-tested network authentication protocol. Instead of sending passwords over the wire, which is incredibly insecure, Kerberos relies on cryptographic tickets. The basics are simple. You have a principal, which is your identity or the machine's identity, and a key tab. Think of a key tab as a highly secure, encrypted file that acts as your password. You use these to talk to the key distribution center and obtain a ticket granting ticket, or TGT. You can do this manually using the kinit command along with your key tab path. Why is this so crucial for Spark? Because in a YRN or Kubernetes cluster, your Spark driver needs to securely spawn hundreds of executors. Instead of distributing your sensitive key tab to every worker node, the driver obtains delegation tokens from Kerberos and securely passes those tokens to the executors. This allows the executors to safely read from HDFS or Hive without needing their own key tabs. This sequence diagram illustrates the brilliant delegation token lifecycle. It starts on the left. The developer uses kinit with their key tab to request a ticket granting ticket from the Kerberos KDC. Once granted, they run Spark submit. The Spark driver then talks to the KDC to fetch delegation tokens specifically for storage access. Here is the magic. The driver sends these tokens down to the executors along with the tasks. Finally, the executor uses that exact token to authenticate against secure HDFS. The key tab never leaves the edge node. Now, how do we actually configure this in the real world? For long-running streaming jobs or scheduled batch jobs, you cannot have a human typing in a password every 24 hours when a ticket expires. We must automate this by passing Kerberos credentials into our Spark submit command. The basic way is using the principal and key tab flags. However, as senior engineers, we must go deeper. We configure the underlying Java virtual machine using a JS configuration file Java authentication and authorization service. By setting spark.driver.extrajavaoptions and spark.executor.extrajavaoptions to point to your JOS.conf and setting use subject creds only equals true, you instruct the JVM to seamlessly handle the Kerberos handshake. This is the rock-solid, production-grade method to ensure your Spark application maintains its trusted identity for its entire lifecycle, completely unattended. Looking at this command construction flowchart, we see the anatomy of a secure Spark submit. From the base command, we supply the key tab and principal flags. But critically, we also inject the conf spark.driver.extrajavaoptions pointing directly to our jos.conf file. All of these distinct configuration paths converge on the right, resulting in a secure JVM boot, armed with the cryptographic materials needed to navigate the cluster safely. Authentication gets you in the door, but encryption protects the actual payload. Let's introduce Spark data encryption. Encryption is the process of encoding data so that it is absolutely unreadable without the correct cryptographic key. In big data, we divide this into two categories: in-transit encryption, which secures data moving over the network using TLS/SSL, and at-rest encryption, which secures data physically sitting on a disk using AES algorithms. Why go through this effort? Because in almost every modern enterprise, it is legally mandatory for regulatory compliance like GDPR, HIPAA, or PCI. Without it, you fail audits. How we achieve this involves configuring Spark's internal properties and linking it to a robust key management service, or KMS. To achieve true end-to-end security, you cannot just encrypt your storage. You must aggressively encrypt Spark's remote procedure call, RPC, channels, the massive data block transfers during shuffles, and even the Spark Web UI. This mind map categorizes our encryption strategy. At the core is Spark Encryption. Branching to the top left, in transit covers the live data veins, RPC channels, block transfers via SSL, and securing the web UI with HTTPS. On the top right, at rest, covers the storage layer, transparent data encryption for HDFS and server-side encryption for S3. At the bottom, we see the drivers for this: regulatory compliance, powered by enterprise key management systems like Ranger KMS or AWS KMS. Let's deep dive into encryption in transit. This is about securing the data actively moving across your network. The foundation requires generating Java key stores, or JKS, that contain trusted TLS certificates for your cluster nodes. Why is this critical? During a Spark shuffle, terabytes of data are blasted across the network. Without TLS, a compromised node could sniff those packets and steal raw data, a classic man-in-the-middle attack. To lock this down, we configure Spark to enforce SSL on all web UIs and enable SSL, simple authentication and security layer, for all block transfers by setting spark.authenticate equals true. For highly regulated environments requiring FPS compliance, you must inject specialized cryptographic libraries. As seen in advanced deployments, we pass JVM arguments like add exports to strictly enforce the use of the bouncy castle TLS provider. This guarantees military-grade encryption over the wire. Look at this network interaction model. Executor 1 is sending shuffled data to Executor 2. Because we have enabled SSL and TLS, the data passing through the network node is heavily encrypted. At the bottom, an attacker running a packet sniffer intercepts the traffic. However, because the payload is cryptographically secured over the wire, the attacker only reads gibberish and our sensitive data remains completely safe. Now for encryption at rest. When your Spark job finishes processing and writes a data frame to disk, that data must be encrypted. Spark generally delegates this responsibility to the storage layer, whether that is HDFS transparent data encryption or Amazon S3 server-side encryption. This protects you against physical disk theft or a rogue admin bypassing Spark and looking directly at the files. How do we configure this? If you are writing to S3, you configure the Hadoop configuration property fs.s3a.server-side encryption key and pass it your AWS KMS key ARN. The storage layer seamlessly encrypts the bits as they land. Furthermore, to securely store the actual API credentials or database passwords that Spark needs, never hardcode them. Always use a JEX key store and map it to your job using the hadoop.security.credential.provider.path configuration. This flowchart traces the path of data from memory to physical disk. When you call write.parquet on a Spark data frame, it passes through the Hadoop file system API. Depending on the storage type, specific encryption triggers. For S3, it applies the SSCKMS key we configured. For HDFS, it applies Ranger KMS transparent data encryption. Ultimately, the data rests safely in heavily encrypted cloud buckets or HDFS volumes. Let's tie everything together with a highly critical real-world use case, building a secure financial pipeline for a major bank processing credit card transactions. The challenge: the data engineering team automated their pipeline but kept hitting a SASL exception, GSS initiate failed error. This error means the Kerberos ticket granting ticket expired and Spark could no longer authenticate. The solution was to implement a headless key tab. They updated their orchestration tool to automatically run a kinit command right before job submission. For execution, they submitted the Spark job with the key tab flag, injected bouncy castle TLS configurations into the JVM for FPS-compliant network encryption, and configured the output to use SSCKMS for Amazon S3. The result: an end-to-end encrypted, zero-trust ETL pipeline that processes terabytes of data with zero manual intervention and easily passes the strictest global banking audits. Let's walk through this production-grade pipeline sequence. The orchestrator initiates the workflow by performing a kinit with a headless key tab, securing a fresh TGT from the Kerberos KDC. It then launches Spark, injecting all our advanced JVM security options. As Spark processes the credit card data, all internal network shuffles are encrypted via TLS. Finally, Spark writes the output to S3, actively passing the KMS key configuration. The data lands securely, completely fulfilling our zero trust requirements. We have covered a massive amount of highly advanced security architecture today. Let's summarize the best practices. First, always automate your identity management. Use headless key tabs for your production jobs to ensure they never fail due to expired tickets. Second, meticulously secure your secrets. Never hard-code passwords in your Python or Scala files. Utilize JEX key stores to load them dynamically at runtime. Third, encrypt absolutely everything. Enforce TLS on your web UI, SSL for your data shuffles, and KMS for your final storage. And closely monitor your token lifespans to prevent GSS initiate failed crashes. Embedding these practices directly into your CI/CD pipelines ensures compliance by default. Thank you for joining me in this deep dive. Please like this video, subscribe to the channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Stay secure and keep learning. This final flowchart represents the ultimate goal, a production Spark job supported by 3 pillars: automated key tabs, JEX key stores, and end-to-end encryption. Together, they create an unbreakable zero-trust ecosystem. And the next step in your professional journey, head over to quicktechie.com to accelerate your career. Thank you for watching.